So, hi everyone, and welcome to this live stream. Today we will be talking about biomarkers, and especially biomarker development in animal health, obviously. And we will look a little bit at um, what biomarkers are and what they are for, and some of the application and new techniques. So let's jump into it. But before we start with the main presentation, a couple of words about us, about Lab4Pose. Lab4Pose is a life science company. We are on a mission to support the development of new therapeutics and diagnostics. Here there's some bells ringing in the distance, celebrating our live stream. Lab4Pose is a life science company supporting development of new therapeutics and diagnostics, especially for companion animals. And we want to help also decrease the use of animals in research, especially for the development of human medicaments. And the way that we do this, our little piece in the puzzle, is by supplying biospecimens. And in particular, we supply the dissociated tumor cells from different indications, from cats and dogs mainly, but also from other animals, healthy cells from many different tissues, frozen tissues or formalin fixed paraffin embedded tissues, blood, biofluids, and then we have a complementary portfolio with ELISAs, antibodies, cytokines, and we also work together with Altis Biosystems to provide a human gut model, which is obviously one of the building blocks for example, an organ on a chip, one of the methods for the future. We hope also to reduce animal testing for human drug development. Okay, so let's start a little bit with biomarkers. What are biomarkers? So the definition that we can find on the internet is a natural occurring molecule or gene or a characteristics by which a pathological or physiological process or disease can be identified, which means basically kind of everything what we can use to identify a particular process and can gives us some kind of signal. Now, obviously, when we are developing a particular biomarker, we want to integrate a biomarker into our process, we have to keep in mind what is the reason we are behind it. What is the reason why we are searching for a biomarker? And let's say there are 3, 4 different reasons, different functions of a biomarker. The first one is obviously a diagnosis, being able to identify the disease when we have the disease. The second point is segmentation of a customer, sorry, the customers of the of the patient. So we're developing when developing a therapy, then obviously we want to understand if our patient would be a respondent, a non-respondent, and this basically is part of the selection of the right therapy for that particular patient. And then the third / fourth part would be to monitor the disease progression. So we want to understand how is this particular disease evolving, and most importantly, we want to monitor the treatment. We want to understand, okay, is the medicament that I'm giving, the kind of therapy that I'm giving, effective? Is giving any kind of response? And here, positive, negative, and it's not just the effect on a particular disease, but biomarkers can be used obviously also in combination. So I might want to look at a particular biomarker to see to look at the efficacy of my particular treatment, but I also want to check for biomarkers of toxicity, for example, to see, okay, it's effective, but is it, for example, damaging my liver or my gut or whatever other tissues, right? Now, depending on what's the reason why we are using a biomarker, we're developing a biomarker, obviously we would be interested in using different kind of biospecimens or in general, are getting different kinds of materials. Some of the biomarkers are relatively easy to get, and because maybe they are in circulation, or so you can detect it from blood or from blood biofluids. Others, they are much more specific, so or much more localized. So we will have to look at the tissue. But in some cases, the kind of biomarkers that I want to see, and we've seen before the definition, depending on what I use this for, it's not just for the diagnosis, but also to understand, to segment my patients and understand, okay, is there a high or a low chance that they will respond to a particular therapy? Then sometimes I also want to check the normal adjacent tissue. Maybe if I have a tumor, I want to check also the cells that are around it, and in general, the tumor microenvironment, what is the composition, maybe also the composition of the extracellular matrix, and any component of the immune system, including infiltrating cells in the tumor. So this is everything, this kind of research is quite biospecimen intensive. But obviously on top of this, the kind of techniques that I would use, they depend a lot from the application itself. And some of the techniques, I think we have been exposed in real life, right? Also first person to them, and others maybe a little bit less. So classical techniques, they would be an ELISA or a qPCR, or a PCR in general. So these are the two methods that we've seen also during the corona crisis, for example, with ELISA being the immunological testing, the one also in the strips, but this is obviously the one that were on the strips was much simpler, was with a chromogenic reagent onto it. The ELISA is working in a more quantitative way with devices and so on, but the concept is still the same. qPCR obviously are much more specific. So for this, they would have a much lower detection limit, but they have obviously other kind of issues. So if I want to identify a biomarker, probably starting with a qPCR would not be the best choice, because since they are so specific, they're not that sensitive. So they would not find other things that are outside their range. On the other side, if I want to get another version, a little bit more specific, but also a little bit more sensitive, I might go for a Western blot, where I see that there's a bunch of proteins maybe on my gel, and I want to stain them differently. But then other techniques that are used are obviously also mass spec, for example. If I want to have a general idea of what are the molecules in a particular sample, they can maybe select later on. If I have already an idea of the particular transcriptomics, what is this? Obviously, at the moment, there's much more advanced technologies that are becoming with the possibility of to manage a big amount of data. Then we have not just the genomics, but the transcriptomics, the proteomics, the metabolomics, even the epigenetics that play a role in identifying biomarkers. And all these things per se, they give really big data set. And the fun part into this, or the interesting part, is trying to make sense out of this data set, and understanding, okay, what's how can I interpret these data? One of the simple ways of seeing this is, if I look at transcriptomics, I basically see a bunch of RNAs that are floating around in the cells, but I don't really have an idea of what do they mean. If I complement this with another technique, if I have, for example, a RNA in situ hybridization, and I see basically this on a slide of tissue, I can also see this like distributed spatially, that is completely a different readout. So I can see basically where that particular transcript is inside the cell. And same thing, if I have an ELISA, then I basically have a general idea, okay, that particular protein, whatever, if I didn't find it in the blood, or maybe find from a cell lysate, then I can find this particular protein or whatever. If I do an immunohistochemistry staining, then I can find it inside the cells and can also study, okay, what is the role of that particular molecule. And so these kind of techniques, they complement each other. We have seen this also in the Corona crisis. Some of the work can be done as this first discovery, and then you can use a second technique to confirm. If we want to make an example outside Corona, we can have the feline immunodeficiency virus. I would do the first discovery with ELISA, then I can make a confirmation with the Western blot. If I want to look for biomarkers, for example, for a canine lymphoma, I might want to start with a mass spectrometry for the discovery, and then narrow it down with a confirmation with qPCR. And so we have different kind of techniques that are basically working in concert, and they can use one after the other to, one, confirm the data, two, gain more information about my particular sample, my particular biomarker, where it is expressed, in which particular situation. And obviously, all these kind of samples is not just about analyzing that particular sample, but also making it a time series. For example, looking at the same patient, the same animal, for example, throughout a long period, looking at different stages of the same disease, understanding what is the variability of that particular biomarker. And here I think that animals in general, like the diagnostics of and the discovery of biomarkers in animals, in companion animals, has a huge advantage comparing to humans, which is the unfortunate, so to say, shorter lifespan of animals. That makes also most of the time the evolution of a particular disease quicker. So it would be possible to, and this is what we, for example, are doing regularly also with our customers that are in the diagnostic space. We get the samples from healthy animals early on when they're basically coming for a control, and we do not see yet if they have a disease or whatever. And then in some years, they would probably, at least a percentage of them, statistically 30% of the dogs and around 20-25% of cats that will develop some kind of diseases, malignant diseases most of the time, that we can use this and get back to the samples that we have stored after we have the pathological, the immunohistochemistry based diagnosis, and then we can look back at the samples that we have and try to find other kind of circulating biomarkers. For example, we can look at cell-free DNA or other kind of biomarkers that I can find around. So let's close it for now. I would just say maybe the where I see that the whole field going, one of the part that would be much more interesting also for the future is a further evolution and complementation of what is at the moment possible with the RNA in situ hybridization, where I can basically track where my transcripts are inside the cells in a particular slide of the tissue. But I think that spatial transcriptomics will bring this to a completely new level. And especially if this is used also for kind of diagnostics. But I'm really excited to see if there would be new techniques that would be, for example, track the movement of the cells inside the particular tissue, the evolution of a particular cell and see what is the significance of this kind of model. And the other point that obviously it's destined to come is AI, the whole integration of these large data sets of transcriptomics, metabolomics data. I think this will for sure lead to completely new types of correlations that at the moment are not at all visible, and where we be able probably to not just identify one biomarker, but probably a whole profile of biomarkers of different transcripts or metabolites that we find in the cells, a kind of a footprint of the tumor, and not just one molecule that might say something, but might not be particularly specific. And I'm particularly, excited about this, and I hope that this will be also something that will come in the future. Good. Having said that, I think we leave the website here for who else want to take a screenshot of the website. You can find us here under the website www.lab4pose.com with 4 written in number. And I thank everyone for being in this live stream, and see you in the next one.